Hello everybody, this is Mike McGinn, your online instructor for NetI 105. Going to talk about Chapter 3 today a little bit to kind of get you going as you decide to dive into the chapter through the NetCAD. In Chapter 3, we are going to begin our discussion of network protocols and communications. A lot of trivia in this chapter. A lot of industry organizations are mentioned in here, and lots of different terminology and acronyms and that sort of thing. So this is going to test your ability to retain information because this is something that as you become an IT professional, a lot of these acronyms and jargon are going to become second nature to you, and it's actually almost like a language in and of its own. Oftentimes when I'm around people that aren't technical and they hear me conversing with another technical person, they say that it sounds like we're talking in the language of acronyms. Well, this is a chapter where a lot of acronyms are mentioned. We will, in this chapter, talk about really the basic nature of communications, and they do a good job in this class or in this module of doing a parallel between communications on a network and a communications, um, between humans. Uh, Here in section 3111, they talk about how any message, even if you're conversing with a person, can be broke down into certain components. You have the message that you want to relay, how you actually relay that message, whether it be sign language, speaking in French, speaking in English, or speaking in street slang, and then the transmission medium. For example, when you're speaking, you're using sound waves. And then on the receiving end, they have to receive the signal, which means that if you're speaking and that person cannot hear, obviously that's going to be a breakdown in communications, but in normal communications you hear the voice of the person that is transmitting the message, and then by the miracle of your brain being able to decipher those sound waves, you are able to basically decapsulate the message that they're sending to you and being able to get the message that they're intending for you to receive. Basically the same thing works with computers. The transmission medium is your network. The signal is your network card, and a protocol stack of some type that governs the rules in which the information is essentially decrypted and encrypted. And of course the message source might be a Word document or something like that, or some sort of application-based message that you want to send. So it does a real good job of establishing those parallels, um, and and then establishing rules. Basically, we have rules in terms of us communicating as humans. For example, when I'm speaking to you, if this was a two-way communication, I might pause and I might say, do you understand? Which is basically my cue to you to say that my message has stopped. Please acknowledge that you've understood my message. That's actually a communication rule that us humans use all the time. Uh, when communication breaks down, which is like when people argue, uh, all of a sudden people are interrupting each other, messages aren't getting fully conveyed, context of the message gets distorted, misunderstandings occur, et cetera, et cetera. So when you're having an argument with another person, you're really, uh, obviously communicating in a poor communication process, because the normal rules of communication uh, tend to be overrun or overlooked, and that sort of thing. Computers can work the same way. There are rules that have to be in place in terms of how can a message be delivered, what is the timing of the message, what is the size of the message that is going to be sent, in terms of the amount of data that's sent with each message, and different formatting and encapsulation processes that are in place to make sure that the message can be deciphered and decrypted by the or decapsulated by the recipient. So they do a real good job of kind of doing those parallels, and it's good for you to understand this whole discussion because of the fact that it really does kind of create the framework in your mind as we get into the more technical explanation of protocols and that sort of thing. So protocols that govern communication, they kind of break it down into 3 layers. There's the physical layer, in other words, how is physically the message getting from the sender to the recipient and vice versa. What are the rules that are involved? And then the content, which is kind of the data payload, the message itself. So in the networking world, these protocols are a little bit more complicated, but really follow the same process. For example, you all have heard of IP addresses that computers have, and that's basically a message destination. And so what happens is in an IP packet, and a packet is kind of the data unit of a piece of data or a message that travels from one device to another based on its IP address. So to do that, there's an IP header that's attached to a packet that says this is where I came from and this is where I want to go vis-a-vis a source IP address or a destination IP address, and then the data payload, which is what is actually the message itself. So that's kind of how things work in the networking world. And then there are also protocols that will communicate on a network that let devices that communicate between devices themselves, not between user applications and other user applications. For example, routers will have protocols operating on the network that keep all the other routers informed as to what pathways through the network are available and what their cost is, in other words, how efficient they are. So that's and we're going to get a lot into networking protocols and later in this course. So they then start talking about the protocol stack, and you may have heard in conversations of other technology professionals where they talk about, well, your protocol stack is corrupt or something like that, which basically means that the drivers or whatever that control your communications has some issue with it. There's basically 4 layers that we kind of deal with in this course of your protocol stack. There's the physical layer, which for a wired network is Ethernet. Then you have a network layer, which is where specific devices have IP addresses assigned to it. And then there's what is called a transport layer that basically handles timing and a lower level application messaging, handshaking, if you will, between like, for example, a PC and a server often are using the TCP protocol to manage the communications for a given application. And then you have the application layer, which in this case they're showing HTTP, which is your web browser. And so what happens is as data is sent to a device, what it's doing is it's traveling up the protocol stack, and then when you send a message back to the sender, you're going down the protocol stack. So the messages are going up and down, up and down, up and down. So why this is important is because of encapsulation of these different protocols, which we will get to here in a little bit. So here we go with the acronyms. Different types of networking platforms have different types of protocol suites and industry standards. What we deal with primarily in this course is IP version 4 and IP version 6, which is going to be over here in the TCP IP column. There's some legacy stuff out there like Novell. If you're in the old Apple world, it's AppleTalk, etc. And basically, as you can see, these are kind of broken up into layers, and they follow the same as I was talking about previously. These are Ethernet layer, or I should say physical layer protocols: Ethernet, PPP, frame relay, ATM, uh, uh, wireless LAN, etc. And then at the network layer, you've got IPv4, IPv6, ICMP, etc. In the Novell world, IPX is kind of the network layer protocol that you run into. And then at the transport layer, again, we deal with TCP and UDP, and we'll talk a lot about those in detail as we get later in the course. And applications that you may be already familiar with, HTTP, which is basically the protocol that handles web browser traffic. DNS, or Domain Naming Service, is another one. DHCP, which is the protocol that handles assigning and managing IP addresses in a network, and FTP, which is a protocol for doing bulk file transfer between two devices. So hopefully through our discussion so far, you kind of get the idea of how networking is kind of broke out into levels, and basically what happens is that that there is an encapsulation process that goes through as messages get formatted to be sent. So for example, if I'm on a web browser, what happens is that web browser is encapsulated into a transport layer data unit, which is called a message, and then that is going to be encapsulated into a packet, and then finally it is encapsulated into a frame so that it can be basically laid onto the physical media that you're going to use to get the message to its destination, whether that be a wired network, a fiber optic network, it's a frame relay network, etc. And the construction of the frame basically varies depending on the medium that its destination that it's destined for. So they'll go into talking about, you know, the history of IPv4 and and why they came out with IPv6. And basically the deal is IPv6 is virtually unlimited in the number of unique addresses you can have, whereas IPv4 is somewhat more limited. So again, this is where the nice little graphic on breaking things up into the different layers of the protocol stack to kind of show you where things kind of line up. And then they go in and talk about more about how the encapsulation works. And as I mentioned previously, the Ethernet is obviously the largest data unit, because that's the last thing that gets handed off to the physical media. And encapsulated within that is the networking information that basically tells that frame ultimately which IP address am I destined for. And then the TCP is basically the handshaking lower application layer information that it needs. And then the HTTP is the specific application that it's destined to, and then of course the data payload. So that's where that encapsulation thing comes into play. So does a nice job of kind of explaining that. You know, it is a little hard to understand if you're just going in and trying to read it, because you get overwhelmed with the acronyms and such, but I'm hoping with this little explanation here, when you read the chapter, it'll make a little more sense. It might even make sense to actually listen to this presentation twice before you start diving into the chapter, because there is a lot here. And there's a nice exercise to drill yourself on for actually getting yourself in tune to, okay, what goes where in terms of where in the four layers of the protocol stack things actually belong. For example, IP is in the internet stack, whereas UDP is going to be in the transport portion of the stack, and that et cetera, et cetera. Ethernet is in the network access stack. So it helps you place these, and then you do a check, and it tells you which ones you got wrong. I would run through this a couple, 3 times, or until you get to the point where you don't have any misplacements of these blocks. And I think that you'll kind of master this pretty quick. These courses do a good job of providing you exercises that kind of drill you on this mundane memorization stuff that unfortunately you've got to embed in your brain. Then they go into even drier discussion about the different organizational standards, and unfortunately in the exams they throw a stray one of these that, to just see if you know it. It's not tested on heavily, but there are a few questions in the exams on some of these. So it's really your judgment as to whether you want to be a master of all the industry organizations and what they do and what they can't, etc. What I'll try to do for the final exam is to kind of clue you into which ones you better know, because there's just so many of them. One that I think you do need to kind of commit to memory is the protocols that are associated to the IEEE 802 working group, and these are used a lot in conversation with IT professionals, that when they converse, like for example, you might be familiar with wireless networking, a lot of different 802.11 standards. You've got 802.11a, B, G, N, etc. And basically, with each revision of the 802.11, you got into faster wireless technology as it evolved. For example, 802.11b, when it came out, was just a 10 megabits wireless network. The G was the 54 when it went up to a 54 speed, and then the N's got even into the faster ones, and I believe there's even some faster standards now too. So this is something you got to kind of know. I don't really see, like, from 802.16 down really tested over much, but 802.11 1 and 3 tends to be mentioned the most. There's a lab on researching network standards in here that you might want to do, and that sort of thing. So then they talk about the layered models that are out there. And there's basically 2 that are heavily referenced. And within the context of this course, we really talk about the TCP IP model. And really the only difference between the TCP IP model and the OSI model is that they basically group the top 3 layers of the model into one layer, which is called the application layer in the TCP IP model. So what we do is we spend a lot of time talking about the OSI model, and then you'll see it kind of flip back and forth between that and TCP IP model in terms of discussions, which gets confusing from time to time. And you basically need to know both and have those committed to memory. And again, know what goes into what block. For example, the PPP frame relay and Ethernet you find in the network access layer, but on the OSI model, they really take the network access layer and break that into 2 separate layers, which is the physical and the data link layer. The physical layer is basically the physical media itself. The data link layer is where the actual frame is identified and constructed. So that's something that is a little bit different. So the OSI reference model, it kind of goes through a description of each one of those and what it's used for. Like I said, we really don't get tested much on 5, 6, and 7, but you're going to have to know 1 through 4 kind of like the back of your hand. And nice little section here about, the comparison of the two, as I talked about, um, and that sort of thing. And then there's a lab on researching RFCs, which are, again, standards that basically govern the way that the TCP/IP models evolved and were identified, et cetera, and classified. And we go into data encapsulation, which we've kind of already discussed, but it kind of dives into that. And the thing that's important is, the physical is the timing and synchronization of bits from the sender and the receiver, so that it knows what kind of bit structure it's getting and how fast it's going to be coming, so it can get the timing down. Kind of like if somebody's talking and one person's kind of slow and the other one talks a mile a minute, you're going to have miscommunications. So, having both parties synced where they are on the same page as to how fast the communication is going to flow obviously makes for better communication. The data link layer is where the destination source physical addresses of the devices is taken care of. And what we mean by that is generally in our world of networking is MAC addresses. Each network card, NIC, whatever, whether it be smartphone or notebook computer, desktop computer, they all have some sort of network interface card or feature that's hardware within it. And each one of those devices has a unique MAC address. There are no such thing as identical MAC addresses and these are generally burned into the hardware itself, into ROM on the hardware. Where we get into the logical addressing is when we get into the network layer, and this is where we're talking about IP addressing and IP schemes and that sort of thing, and that's where we basically marry an IP address, which is specific to that particular network, to that particular MAC address. And that's logical, so that way routing can occur much more efficiently, and then we'll get into more of this later in the chapter. And then the destination and source process numbers or ports in the transport layer is really just talking about, okay, once I get there to my actual physical machine, wherever it is, and where do I put it in terms of feeding whatever application needs this information? And then the upper layers basically as the encoded application data. So again, they talk a little bit more about the data link layer and the network layer and why you've got a unique data link address, and the IP header is, or the IP packet is what really is the logical aspect of that. Then we get into the concept of a default gateway, which is getting into the network layer, and basically what happens is, and you may notice you've got a default gateway on your computer, and what the default gateway says is that if I want to send something to an IP address, which is a logical network layer address, and that logical network layer address is not on my local network, my local physical network, or my LAN, where do I send it? Well, that's usually your gateway, which in most cases on small networks is your router, your internet router. And so they kind of talk about that concept, and that's basically about it. And there is a lab here on using Wireshark to view network traffic, which is kind of cool. It lets you actually see what we're talking about, being able to decipher network traffic. So again, that's pretty good here. Now, in our let me get to where I want to go here. Our assignments for this particular chapter is building a simple network lab. This is where we're actually going to, as if you had a bunch of physical PCs and servers and stuff sitting in your basement, putting it all together and getting it all to talk. And then the lab 3441 is using Wireshark, so you can actually, with this piece of software, go in and examine the packets or frames that are going through the network, and that sort of thing. So that's kind of what we got going on in Chapter 3 this week. So it's a kind of a tedious chapter at times, but I urge you to put in the work to try to master as much of it as you can, because it pays huge dividends down the line, because it gives you that theoretical framework you need to be able to think logically and to be able to troubleshoot, knowing where your problem is. When you've got a problem with network communications, and being able to figure out, okay, do I have a layer 1 problem, which would be a physical problem, physical media problem? Do I have a layer 2 problem, which is going to be my network drivers or et cetera? Do I have a layer 3 problem, which means is an addressing problem or a routing problem on my network, where there's nothing wrong with my devices, it's just my intermediate devices such as routers, switches, etc. Those things are messed up. Or do I have a problem with the applications themselves and the handling of those source and destination recipients and senders? So again, like I said, there's a lot of acronyms and a lot of memorization kind of involved in this chapter, but like I said, if you kind of understand what's what, it's going to pay you huge dividends later in the course. Okay, so that's all I got for now. So I will have more later for you on chapter 4. So, or chapter 4, because this is chapter 3. All right, have a good week.